Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and a very warm welcome to the third lecture of week 10. Today we are going to start chapter number 5, which is currents and conductors. So since we are dealing with currents, it means that now we are departing from the electrostatics situations, because we all know from our basic electricity and basic electrical engineering courses that uh, current is nothing but movement of charges, as we normally consider it to be like this. However, more precisely, in physics, it has been defined as the rate of change of current. So movement is not really necessary. The change is really something which we should be looking for. So there are a couple of things which we must understand before proceeding to understand magnetostatics. So this chapter and the chapter next to this one, especially this chapter and initial portion of this chapter, especially this lecture, should be treated as a prelude to magnetostatics. So before discussing or diving deep into magnetostatics, we should first make few concepts about currents clear. And whenever there is current, there is always conductors. uh, at least this is how we start the discussion of currents, because initially we try to think that current is movement of charges within certain material, and definitely movement of free charges, and the only material which offers naturally the huge amount of huge concentrations of free carrier is conductors, or metallic conductors to be precise. Okay, so metals are the uh, metals are the materials which are capable of providing huge concentrations of free carriers. That's why they are called conductors or electric conductors, because they have got the ability, metals have got the ability to conduct electricity from one side to another side of a circuit or a system. So so far the definition of current which we are aware of normally, because of overexposure to circuit theory, is that current is the rate of movement of charges passing through a reference point or crossing a reference plane. So this is a true definition, no doubt. So rate of movement is something which in which we try to think about the current. So it is not necessary that charges are moving in order to constitute a current, and this is something which we will see shortly. So consider this three-dimensional plane, for example. Z-axis is coming out of the board, and these are the positive charges, and let's consider that the charges are moving perpendicular to y-axis and parallel to x-axis. So if charges are moving in this direction, and according to this definition which we all are aware of and are comfortable with, that if I'm standing in the middle of this whole scenario, and if I consider a plane uh, z equals to constant, sorry, x equals to constant plane, and if now I start noticing the amount of charge which is moving from left to right as shown by this arrow parallel to x-axis, and if I somehow calculate that charge which is moving across this plane and divide that charge by the amount of time over which I have observed this movement, then the ratio of the charge which move across this plane divided by the time of observation in seconds will give me the current. So or if perhaps if I choose to observe the amount of charge which is moving from left to right in 1 second, then that amount of charge would be current, because I'm measuring that amount of charge or observing that amount of charge for 1 second only. But the major, I won't say problem, but I would say the major implicit, assumption in this whole scenario is that the plane which I have considered, this is obviously an imaginary plane. The plane which I have considered, which we have considered imaginary plane, over which we are observing the flow of charges, is always oriented in such a manner that the charges are always perpendicular to that plane. This is perhaps because of the reason that normally we consider that this, if for instance this is a conductor and current through this conductor is in this direction, so obviously we try to think that charges are moving from left to right. This is how we like to think. And if I ask you to imagine a plane, you would definitely imagine a plane which is perpendicular to the direction of current. This is how we try to look or observe the current. So that's exactly the reason why we do this. By the way, I am choosing positive free charges just to be consistent with our conventional definition of current, in which positive charges are moved, although it is not physically the reality in conductors. So if this is the case, then we say that okay, current is in this direction, and to emphasize that the direction of the current in this particular scenario is along x, I would say that Ix is nothing but the amount of charge which moved from left to right along the direction of x in 1 second. Okay, that will be current. But remember that current, the true definition of the current is this, all right. But current can, number one, current can also be defined by observing movement of charge through a particular point. It is not really necessary for me to define a current. I must define a plane. No, I can define a point as well, and observe how much amount of current is passing through this point in 1 second. Then that amount of charge which is passing through this point in 1 second would be current. Or if I choose to observe this point for a different time, then the amount of charge for that time divided by that time will give me the current. Okay, so one thing should be clear, that it is not really necessary to observe a plane. Point can also do the job. Or you can think of this scenario, a point, observing charge through a point, to be considering a plane, cross-sectional plane, to be of so small area that that plane can be treated as a point. So one thing should be clear, that to define a current, reference plane is not really necessary. Current can be defined by observing movement of charges through a point as defined here. Later on we'll discuss that. We'll not really discuss rather we'll discover that movement is not really necessary to constitute current. A random change in charge, in the amount of charge, also constitutes current. It is not really necessary for charges to physically move from one point to another in order to constitute current. For instance, in the case of parallel plate capacitor, we all know that or any capacitor, we know that there is really no conductive medium between positive plate excuse me, and the negative plate. But current passes through that. Is that if this is the only definition which we are exposed to, and if this is the only definition of current, in that case Current should not flow through the capacitor because there is no conducting medium, but current is not really the rate of movement of charges from one point to another, through one point or through one plane. Rather, it is rate of change. More accurately or correctly defined definition of current is that current is nothing but rate of change of charges. If, for instance, let's say this is a point charge of 1 microcoulomb at, let's say, time t is equals to 0 seconds, and after 1 second, let's say at time t is equals to 1 second, this point charge changes its value to, let's say, let's say 2 microcoulombs. So in this case, now the current will be 1 microcoulomb plus divided by 1 second. The current will be 1 microsecond. It does not really matter that how much charge was moved from here. Is somehow magically I do some magic on it, and over 1 second the amount of charge at this point doubles. It means that there has been some current flown from my magic wand to this point. The mechanism we don't really know, but you should remember, if this is a point charge and you can see there is no way of flowing current, but charge is changing its magnitude somehow through any mechanism which we are not aware of as yet. So in that case we will say that current exists here. ठीक है, अगर चार्ज वैल्यू चेंज कर रहा है, भले चार्ज मूव होता हुआ नजर नहीं आ रहा, चार्ज ओवर द पीरियड ऑफ टाइम वैल्यू चेंज कर रहा है, तो हम कहेंगे कि इस पॉइंट पर करंट है मौजूद. ठीक है, सो द करेक्ट डेफिनेशन वुड बी द रेट ऑफ चेंज ऑफ करंट, the rate of change of charge is current, really not the rate of movement of charge, is not really the complete definition of current. All right, so how about, so in this picture the most important implicit assumption is that the plane which we are considering is perpendicular to the flow of current, flow of charges. Since we have made this choice, and what we do normally, we forget that we have made this assumption. So what we really we are tempted to do, हमसे होता क्या है, होता ही है, what we are tempted to do is that we consider that the direction in which charges are moving is the direction in which current is there. But remember that current is not defined by the direction of charges, rather it is defined by two entities: the direction in which charges are moving, number one, number two, the orientation of the plane which you have considered. Had you considered a plane like this, for instance, not like this, like this, had you considered a plane like this, and had you observed how much charge is moving through, crossing through this plane, and let's say the charges are moving in x direction only, perfectly in x direction, the current would be 0 through this plane. Why? Because no charge is crossing that plane. However, instead of considering this plane, had you considered a point and observed the movement of charge through this point, then that observation, that change or passing or crossing of charge through this point per unit time would definitely give you current. Okay, so with this I would now proceed to define current density. And current density, by the way, is something which is dependent on charge, motion of the charges, or direction of the movement of the charges. So now let's keep our focus on the definition of current in which movement is of charges is there. Let's keep our focus on this type of current particularly, which we are more used to of. In this definition, however, this mathematical definition is still true. Okay, in this particular scenario, in which we consider that the charges are physically moved from one side to another side, crossing a particular reference plane or a point, this definition mathematically it's true. So let's keep our focus to this type of current in which charges are physically moved from one side to another side of a reference plane or a point. In that case, how do we define current density? Because our topic is current and current density. We have discussed quite much on current, but current density is something we should be, we should make ourselves familiar with. So it is well be possible that this, let's say there is a huge conductor in this x direction, and I'm showing you just one portion of that, in which charges are moving perpendicular to a reference plane. So how would we define current density? We will define current density by the ratio that the amount of current through this surface area of this reference plane, if we take the ratio, we'll get current density. And now you might have guessed that later on we'll apply a limit to this delta S tending to 0. It means that we will reduce this plane to a point, all right, and we'll try to define current density at a particular point. And you are going in the right direction. You should have guessed it by now, because whenever we have incremental entities, we try to reduce it. You might have guessed it by now. All right, so since the assumption in this particular situation is that the direction of current, that is I, is perpendicular to what? Surface area. So in this case, especially in this particular figure, the current density which we are defining is actually normal to the surface. So just to emphasize this fact, I'm just appending a capital N in the subscript. Okay, so if you cross multiply it, so you'll get this. I'm getting rid of the bars and everything, where this Jn magnitude is the magnitude of the current density. Density kasafat kya hai? What is the kasafat? Density of current. So definitely if current is more dense over a surface, so numerator will increase and the surface would remain the same, approaching 0 later on. So current density would increase over that very small surface, which will be converted to a point later on. So if more current is passing through a point, we'll say that current density is more at that point. All right, so but in this definition, one thing is implicit, is assumed that current is perpendicular to what? To the direction of current is perpendicular to what? To surface. But remember that current is a scalar quantity. There is no direction associated. So direction will not be associated with the current, rather it will be associated with the current density. So the direction of motion of the charges is perpendicular to this surface. In this particular case, we can define that the current density is the amount of current, that is the number of charges flowing through this imaginary surface, divided by area of that surface. This will give us current density. If we cross multiply current density by area, we'll get what? We'll get uh, current which will be passing through this incremental area. So remember, I'm showing you the picture of a bigger conductor in which this is happening. So this is a small portion of the big conductor. That's why we are talking in terms of incremental areas and incremental currents. Now, if this is not the case, if let's say charges are moving in this direction, and let's say I have assumed this to be the surface area. Now, how would I define current density in this case? In this case, since I know that for perpendicular case, current density is defined as this: the current amount of current passing through the surface area divided by the surface area. So if I had changed the orientation of the surface area, would the current change? Definitely the current would change. But how about the amount of charge moving from left to right? That would be the same. Had I considered this plane, okay, how much amount of current will be crossing this plane? 0. So, and how much is the surface area? Non-zero. So 0 divided by non-zero will give me 0 current density, 0 it will give me what? It should give me sorry, yeah, here. And since the charges are moving from the left to right, so the J, the charge density, or sorry, the current density is not 0. But since the orientation of the current density is such that with respect to the plane of observation, that there is net 0 current here. So no current is flowing through this. No current is flowing through this plane does not mean that charge is not moving. So the movement of charges is not associated with current, rather it is associated with current density. So for such cases, we know that we use dot product. For this plane of observation, current density is Jn, all right, and current is non-zero maximum. For this current density, for this plane of observation, current density is non-zero but current is 0, all right. So this is what we are getting when we are taking plane like this, and we are getting 0 if we are taking plane like this. How about if we are making some angle which is between these two extremes? In that case, we'll have to take dot product, all right. So now you know why we do it. Okay, so if I apply the limit that surface is so small that it can be treated as a point, we'll convert the incremental entities into differential entities, and if I integrate this over the whole surface area which is not closed, so in that case we'll get equation number 1, and in this equation number 1 we are getting I, that is the current measured in amperes, and that is equals to surface integral of J dot ds. So since this J is defined with this particular scenario in which we consider that the charges are moving, all right, so that particular current actually is known as convection current, in which charges are moving. You know, recall the modes of heat transportation: convection, radiation, right? So similarly, mode of electricity transfer, if it is through physical movement of charges, we'll say it as, you know, convection current. If it is through wireless communications, where there is no physical current or charges moving, in that case we'll say that the energy is radiating. Anyway, that's a topic of later chapters. All right, so this is the current through current density. The relationship between current and current density is given by equation number 1. So J is defined as the units of J are amperes per meter square. You can see it from here for a particular case. All right, amperes per meter square, how much dense a current is across a particular surface area. So how to calculate this J? How to calculate this J? Calculating J is something which is remaining so far. So let's try to discover that. All right, so now to calculate J, or the formula for J, by the way, as a teaser, I told you before that J, or the current density, is something which should depend on the direction of movement of charge. So we should expect something which would be relating J to the movement of charge. All right, since this J is defining convection current, and convection means charges are moving, so J should have something related to charge. So for this derivation, let's consider a conductor which is oriented along x-axis and carrying a DC current in this direction. All right, and DC current, why we have assumed that? Because in every derivation we try to start things with least possible maximum possible assumptions, and then we'll try to generalize things. So we could have taken the conductor in any direction, but that would not serve the purpose. So we have oriented this conductor along x-axis and chosen to flow the current DC current through it in this direction along the x-axis, but going from positive towards negative. Choosing DC current means that the charge density theoretically within this this conductor, throughout this conductor, would be constant, because this is DC current. It is not changing with respect to time or with respect to distance along the conductor. So one thing is clear, that current is moving in this direction from positive x to negative x, and it is DC, meaning that charge distribution throughout this conductor would be the same. It means that what the picture which I am trying to show, definitely charges are moving in this direction, in the direction of current. It is, the charges are moving, but what do I mean by constant rho v? By constant rho v means that I'm showing you this picture at a particular time, let's say t equals to 0, when we started to observe this whole scenario. And at t equals to 0, I've considered this differential, this incremental box of volume rho v. All right, so the depth of this box along x-axis is delta L, and let's say the face, the front face or the back face of this box has got the surface area delta S. So I can say that the volume of this differential, this incremental box, is delta S into delta L. All right, so definitely charges are moving through this imaginary box as well, but at time t equals to 0, there must have been some charges within this box, and let me call the charge which is in this box at time t equals to 0, let me call that charge to be delta qi for internal. Okay, so if I want to calculate that charge which is inside that box, I can simply multiply rho v by delta v, which is the volume. So I can replace delta v to be delta S into delta L. All right, so after some time, t equals to, let's say, delta t, a very small time, definitely charges, the box is in place, the charges will move from this side, front side, to back side of the box, definitely. So if I want to figure out how much amount of charge has crossed the front surface or the back surface, because we are considering DC current, so rho v is constant. So the amount of charge which has entered through the front surface will be equals to the amount of charge will be which have left from the back surface. So excuse me. So to analyze the amount of charge which has moved through any reference surface, which is given by delta S, within this time, what I can do, I can either stand here and try to observe how much amount of charge has moved through the front surface, or the other method is, instead of moving the charges, I can stop the whole situation, take a snapshot, picture ले लूँ, उसको pause कर दूँ, and I should move this box rather this box I should move with the same velocity with which the charges would have moved. या तो चार्जेस को रोक दें, डब्बे को उस हिसाब से मूव करें, उस रफ्तार से मूव करें जिस रफ्तार से चार्जेस मूव कर रहे थे, या डब्बे को रोक के रखें और चार्जेस को चलने दें. बोथ have got the same meaning. All right, either you stop the charge and move this box with the same velocity of the charges, or keep the box at its place and let the charge move with its own velocity across it. Anyway, what we need to find is the total charge which is crossing the front surface or the back surface. Okay, so let's say after the time delta t, the box which was moving with the speed of charges has moved a distance, let's say delta x, after time delta t. This is the distance which it covered. So the amount of charge which crossed the front surface or the back surface would be the same. So the amount of charge within this shaded box, which I drawn at the back of this main box, the amount of charge within this shaded box is actually the amount which has been crossed, has crossed the surface at the back, and that would be this exactly the same amount of charge which passed through the front surface, because we are dealing with constant rho v. So this would be equals to rho v multiplied by this area with this volume which is shaded, and it is given by delta S times delta X. Okay, yeah, all right. If this is the charge which moved out of the box during time delta t, then we can say that the differential amount of current which moved through this surface is equals to delta q divided by delta t, because this much amount of charge has moved the reference plane within this time. So rho v delta s into delta x, this is delta q divided by delta t. So what is this? The distance which this box covered in x direction in this time. So this is nothing but rho v delta s. This is nothing but velocity of the box in x direction. All right, and by the way, this velocity of the box is the same velocity with which the charges were moving, because as we said that either keep that box within its place and let the charges move with their normal velocity, which is Vx in this case, or pause all the charges and move the box. So the velocity of the box or the velocity of the charges are the same given by Vx. Okay. All right. So if I cross multiply it, so current, incremental current divided by incremental surface area is equals to J. We all know that J, and this is equals to rho V rho V Vx. And just to emphasize that since charges are moving in x direction, so the current density would also be in x direction. Just as previously we said that when we defined the current density, we said that current density, magnitude of current density is given by what? Delta I over delta S, and we said that there is one assumption that the charges are moving perpendicular to the surface. All right, that's the reason why we said that we are appending capital N here. Is it? So from here we said that charges were moving normal to the surface area, so the current density was also normal. All right, so if charges are moving in x direction, the current density will also be in x direction. And we know that generally, if this was a particular case, generally if charges are moving in v direction, and to emphasize that direction, we should take v or the velocity as a vector quantity. Here the direction was implicit that the charges are moving in x direction, so we did not bother taking v as a vector entity. But generally the direction in which charges are moving can be in any direction, so we'll consider that direction by considering velocity to be a vector entity, as it is a vector entity. And if we multiply that the velocity in which the charges are moving by the charge density, we should get what? What should we get? We should get the general formula for current density, which is this convection current density. So you can see that coulombs per meter cube is charge density multiplied by meter per second is velocity. So meter cancels meter, so it becomes a square. Coulombs per second is amperes. So we've got amperes per meter square as the units for J. All right, so this is how the current is calculated if J is known, and how to calculate J can be calculated using this definition. Now see, you can see that the direction of J is the same as direction of the charges in which this charge density is moving. All right, so this is how we calculate the current density in its vector form. So before concluding this lecture, I would like to discuss a very important relationship which is known as continuity of current, or the equation which we'll get at the end of this topic is known as continuity equation. So far we have discussed two equations, one for convection current and one for convection current density. Now for continuity of current, let's consider a volume. All right, a volume which is surrounded by this closed surface, volume which is enclosed by this closed surface. And let's say I somehow inject positive charges, which I'm calling Qi, at time t equals to 0. All right, as soon as I inject these charges within this volume, what I'm going to get is a charge density within this volume, rho v. and that may be a function of space within this volume. All right. After injecting, now I start observing how the charges behave. All right, so they are not fixed charges. I have took an injection and filled that injection with positive charges and injected, let's say, those positive charges, how much qi charges within this, or the injected charges. All right, or the charges within this volume. So as soon as I did this instantaneously and left that volume alone to observe it, so what will happen? These positive charges will push each other because they're positive charges, repel each other, and the charges will try to come out of this volume through the surface. And if I want to find the charges, the rate with which the charges are coming out of this volume, since I am interested now in the rate of charges coming out from this volume through this surface, what I can do is I can apply equation number 1, J dot ds, applied over this surface. And since that surface is closed, I'm using this closed surface integral. Generally in this equation number 1, there is no closed surface integral assumption, but for this particular case there is an assumption that the surface is closed, obviously, because I am considering a volume. All right, so now definitely charge density, since charges are changing with respect to time, so charge density will be changing with respect to time, and charge density would become the function of time. So this is the current which is coming out of this closed volume. Okay, because as soon as I started observing it, charges are coming out with certain rate of this volume or this closed surface. So current has been constituted, which should be equals to the rate at which the internal charges qi or the injected charges are decreasing within the volume. Decreasing, that's why minus sign. So this much amount of current is coming out. If I'm outside that volume, I can say that this much amount of current is coming out of that volume, which should be equals to the rate with which charges are decreasing within this volume. This is known as law. This is according to law of conservation of charges. All right. If that's the case, and now we have discovered that this J has got velocity in it, so it means that J belongs to flux density kind of vector fields. All right, so this flux density type of vector fields J is dotted with ds and is integrated over a closed surface. It means that it is Gauss's law. All right, in Gauss's law, and in the case of electrostatics, the Gauss's law had D here, which also belongs to flux density type of vectors, and this J is also flux density type of vector because it has got a sense of movement in it associated with that. All right, it means that we can apply divergence theorem here, and divergence theorem tells us that this can be replaced by this, where remember we said that there is a connection between this volume and the surface, that this volume is the volume which is occupied by this surface. So what we can do here on the left hand side, apply divergence theorem. I can do this. Which is equals to minus d upon dt, and qi is what? Qi is rho v rho v. We know that q is rho v dv volume, right? So integral rho v dv, instead of qi, I can write this volume as this volume, obviously. This volume is the same volume. Both sides have got the same volume integral over the same volume. Since volume is not changing with respect to time, so time is a constant for volume for this integral, so I can take it inside. Okay, so I'm taking it inside of the integral sign. So while taking inside, I'm also doing a Bemani. I'm converting this rate of change, a normal rate of change, by partial derivative. Okay, and on the left hand side, let's choose not to do any Bemani now. Why I'm doing just Bemani here? Because we'll talk about that later. Okay, so if this is equals to this, it means that this entity is equals to this entity. Both are equal. Okay, so if that's the case, del dot j is equals to minus, this is a very important relationship known as continuity equation, and it says that divergence of current density is equals to the rate of decrease of charge density. A very commonsensical kind of relationship, right? The rate with which the current is coming out of this volume is exactly equals to the rate of decrement of the charges within this volume, right? So this thing which I have written here, this is what current, if I observe that volume from outside that volume, this is the current which I'll see which is coming out of the volume, which should be equals to the rate of decrement of the charges within that volume. This is something which is evaluated over a macroscopic level. But if I want to evaluate the same fact at microscopic level at each point, what should I do? I should use equation number 3, because what we have done, we have taken that macroscopic phenomena and we have left the integral sign and the variable over which the integration has been performed, and we have taken the integrand only. All right, the integrand only, and integrand is actually something which is defined over a very small entity or a point, which after integration gives us the macroscopic entity. Is it? So equation number 3 is nothing but point version of this commonsensical thing, that the current which is coming out of the surface is equals to the rate with which the charge is decreasing within the surface. Or if we talk the same fact in terms of differential entities, or in terms of a point, we will say that current density, divergence of current density is equals to, at any point, divergence of current density at any point within this volume is equals to the rate at which charge density is decreasing within this volume at the same point. All right. So after this step, when we have done this step, what we have done actually is that we have practically applied a limit that this volume is tending to is so small that it's tending to zero. It can be treated as a point. So the current coming out of a point, you can say, try to imagine this sphere to be so small that it can be treated as a point. So you can say that the current which is coming out of that point is equals to, or the current density, I should say, which is coming out of the point is equals to the charge density which is reducing within that point. So this is how we try to define it. So as we all know what divergence gives us either source or sink of the field. So it tells us basically whether a point is a source or a sink, or it is neither a source nor a sink of for that particular field. In the case of electrostatics, we said that if you evaluate this divergence of electric flux density, you will get a non-zero value, a positive value, if that point over which you have calculated the divergence, if that point there is a positive charge, you will get a positive value. It means that that point is originating electric flux. But we did not talk at that time in terms of electric flux. Rather, we talked in terms of electric flux density. Same is the case here. Evaluating left hand side tells us evaluating left hand side, which is divergence of current density at a particular point, tells us whether that point is source of current density or not, whether that point is originating charges or flow of charges or not. If that is true, if that point is originating the flow of charges, then that flow of charges would be equals to the rate at which that charge density would be decreasing at the same point. All right, so this is a physical sense to it. So with this, I would say thank you, and let's say if this divergence comes out to be zero, it means that that point is not originating any movement of charge, or if that point is not originating current or movement of charge, then there is no rate of change of charges at that particular point. So that point is neither a source nor a sink. And if it turns out to be negative value, divergence, it means that that point over which you have calculated the divergence is the sink of current density, meaning that at that point charges are coming in, all right, and they are staying there. So that point is source of that point is sink of current, because charges are coming in and they are staying there, they are no more moving further. It means that that particular point is the sink of what? Sink of current, because current is terminating at that point. You can think of it like this, and in that case you'll get negative value, all right, of the divergence. All right, Assalamu alaikum.